Hey guys, my name is Akshay and I'm going to be presenting my findings for Lab 2. Overall, Lab 2 is very similar to Lab 1. We followed the exact same procedure of creating charged tapes by peeling two pieces of tape off one another. We also did the floating tapes experiment and found the floating distance. Our goal in this lab was to determine the charge on the tapes. This time around, we modeled the situation differently, which would change the value of Q. The physical principles that we saw were neutral charges attract both positive and negative charges. Like charges repel and opposite charges attract. Objects can acquire an excess or deficiency of negative charge through transfer of electrons. Newton's third law, which states that we have equal and opposite force pairs. Newton's second law, which states that F equals ma. And finally, the superposition principle, which states that the net electric field is going to be the sum of the electric field contributed by individual point charges, and that the electric field contributed by one point charge is independent of other point charges. The superposition principle was key in our computational model, which we'll see later. Here's a quick summary of my results. The tapes used were 8 inches or 20 centimeters. Both the tapes were negatively charged. The mass was about 0.0002 kilograms, and the floating distance was about 0.02 meters. These are the calculations that I did to determine what the charge on the tape should be if we are assuming that all the charge on the tape is centered in the middle of the tape as a point charge. I set the gravitational force to be equal to the electric force, and that will give us the expression k times q squared divided by d squared equals 0.00196 newtons. From there, just solve for q, and that will give negative 7.4 times 10 to the negative 9 coulombs, since my tapes were negatively charged. This Q value is going to be used as a reference value to compare to the Q value that we will get from the computational model. So let's move on to the computational model. Our computational model was different from the model in Lab 1. We didn't assume that the charges were centered in the middle of the tape, but instead we divided the top and bottom tape into a series of point charges. After dividing tapes in this manner, we iterated through each point charge on the top tape, and by setting each particular point charge on the top tape as an observation location for the 10 charged points on the bottom tape, we found the net electric field at each point on the top tape. We also kept track of the net electric field of the top tape as a whole, which was the sum of all the electric fields of all the points on the top tape. By doing so, we could find the value of the electric force and modified our Q value until we found the magnitude of the electric force to be equal to the magnitude of the gravitational force. The Q value discussed earlier was negative 7.4 times 10 to the negative 9 coulombs, and the Q value that I found from using this model was negative 1.184 times 10 to the negative 9 coulombs. This slide here is a visual of my computational model. Each of the green arrows represents the net electric field at that point adjusted by a scale factor so that it will appear more clear. Note that the arrows point downward since the charge on the tapes is negative and the direction of the electric field is going to be towards a negative charge. The white arrow represents the direction of the electric force vector. Since the charge on the tapes are negative, you're going to have F equals negative QE, meaning that the electric force vector points in the direction opposite to the arrows of the electric field. The yellow vector represents the direction of the gravitational force vector. Gravity is defined to be downward toward the Earth, so the direction in the picture makes sense. The computational model heavily draws on the physical principles that we discussed earlier. By dividing the tapes into point charges and calculating the net electric field at each point charge on the top tape, we are directly using the superposition principle, since the electric field at each point charge at each point on the top tape is going to be the sum of the electric fields contributed by each of the point charges on the bottom tape. To calculate the magnitude of the gravitational force, we use the equation F equals mg, where g is the gravitational constant for acceleration, so this is just Newton's second law. Also, when we changed our Q value to match the magnitude of the gravitational force, we did this because Newton's third law states that we are going to have equal and opposite force pairs. Finally, the result of the floating tapes was possible because electrons can be transferred between tapes, and in doing so we created two like-charged tapes which repelled each other. Now, of course, our lab did rely on some key assumptions. We assumed that both tapes had the same charge evenly distributed as n point charges along the tape. We assumed that air resistance was negligible. Another assumption was that the n point charges on the bottom tape did not have any interaction with each other, only the point charges on the top tape. And finally, the neutral atoms of our hand did not affect the point charges on the tape. To wrap up, using the same procedure as Lab 1, we were able to get a different Q value from our computational model. Our Q value in Lab 2 is going to be more realistic because charged objects are not point charges centered in the middle of the object. Depending on the type of object, we can expect the object to be composed of many different point charges. Alright, so that is the end of my Lab 2 video. Thank you guys for watching.